Hello everyone. Today we have an exciting topic that is block cipher cryptanalysis. But block cipher cryptanalysis is a very huge topic. I even teach a course named Applied Cryptanalysis, and even there we can only barely cover some of the topics. So today it will be a very brief overview of the topic. So let's start with an introduction and see some of the definitions. Let's talk about attack types. So total break is actually the attack type in which the attacker recovers the key. So you might think that this is always the case, since in cryptanalysis we are trying to break a system and block ciphers have a secret key. So the aim of the attacker should be capturing the key. But this is not always the case. This is not always the types of attacks, but this is the main thing that we want, because once you capture the secret key, this means that you know everything. You can impersonate the people who are talking, or you can listen to every communication. So generally, this is the main aim. But sometimes you can do something similar to that, which is global deduction. In this case of attacks, the attacker finds an algorithm A that is functionally equivalent to the encryption with the secret key that you don't know, or the decryption with the secret key again, which you do not know. So you find something equivalent to the encryption algorithm with the secret key. And sometimes you can do a local deduction. In this case, the attacker can generate the plain text corresponding to a previously unseen ciphertext or vice versa. So you cannot listen to every communication because you don't have the key, but sometimes you can generate a ciphertext from a plain text which nobody encrypted before, but without knowing the secret key. If you can produce the ciphertext as if you knew the key, then it will be a local deduction, or you can do the vice versa. And finally, the thing is the distinguishing algorithm. This is the last but not the least. The attacker can effectively distinguish between two black boxes, and these two boxes are as follows. First one, the block cipher with a randomly chosen key. Second, a randomly chosen permutation. So this is actually important. So I want to stay here spend a few minutes here, because every attack actually starts with a distinguisher. So we first need to understand what the distinguishing algorithm is. So assume that you are given a black box, in which case you can put input to this box and it produces some output. Now we are asking you if this black box is the block cipher, for instance AES, with a key that you don't know, or it is just a random permutation. Can you distinguish which one it is? So if you can distinguish, then this means that you can distinguish the block cipher with a random permutation. So this is a huge thing, because if a block cipher is good, the output should look random. So it will be impossible for an attacker to distinguish it from a random permutation. So if you can do such a thing, this would be wonderful. And this is also further important because every attack, as I told you before, starts with a distinguisher. So for instance, we know that AES algorithm is of 10 rounds, but if you can find a distinguisher for 8 rounds of AES, not 10, this means that you can distinguish 8 rounds of AES from a randomly chosen permutation. But if you have such a distinguisher, we can use that information to capture the remaining 2 rounds of round keys of the 2 rounds, so you can break the whole cipher. So this is how actually cryptanalysis works. You are trying to find a property, a statistical property that is different for the cipher than a random permutation. Then you use that information to break the cipher. But this will be more clear when we talk about differential cryptanalysis. So today's lecture will be about actually first some definitions and generic attacks. Then as an example, I will talk about differential cryptanalysis. And finally, I will talk about the success probability of these statistical attacks and the data you need to perform the attack. So there are a lot of different cryptanalysis techniques, but we will briefly mention differential cryptanalysis by giving an example on present, and there we will use a distinguisher and perform an attack and see how it works. But these are generally types of attacks we generally consider. So let's look at the data types. So as an attacker, you need to capture some information to perform the attack. So you need some data, and there are different types of data you can capture. For cryptanalysis, attacker may need different types of data. First, the ciphertext only. This means that if you can break a cipher just only using ciphertext, then we call them a ciphertext only attack. And this is in theory always possible because in the beginning we assume that the communication channel is insecure. So we are assuming that the attacker always captures every ciphertext that we communicate. If the cipher is really bad, then the attacker can use only these ciphertexts to break the cipher. But modern ciphers most of the time are resistant to this kind of attack. So most of the time for cryptanalysis, we need more data. And for this reason, most of the attack types, some of the attack types, are considered as non-plaintext attacks. So in this case, the attacker captures some plaintext blocks and also knows the corresponding ciphertext blocks without knowing the secret key. By using this information, the plaintext and the ciphertext, if the attacker can capture the key, then they can perform a non-plaintext attack. And then we have the chosen plaintext scenario. In this case, we are assuming that the attacker has some control over the plaintext that they capture. And 4 is adaptively chosen plaintext. We'll actually briefly mention about them in the following slides, but in the adaptively chosen plaintext, the attacker has some knowledge of plaintext in some format and the ciphertext, and then maybe perform some operation on this data, and then ask for more plaintext. But the type of plaintext they require depends on the computation they performed on the previously known plaintext and the ciphertext. So, as you can understand from what I said so far, collecting data becomes harder as we move down the list, because it was the easiest at the ciphertext only attacks, because we always assume that the attacker can always capture the ciphertext. But when we move down to the list, it becomes somewhat unrealistic. But let's start to talk about them in detail. Let's start with ciphertext only attacks. The attacker has access only to the ciphertext, and this is always possible. Since the communication is assumed to be performed on an insecure channel, this is the most realistic scenario. To perform a ciphertext only attack, the cipher should have significant weaknesses, and we can give examples like RC4 and A51, and we can break these ciphers only from the ciphertext. And if the key size is short, then you can always break a cipher from the ciphertext, because you can perform a brute force attack. Let's move on to the non-plaintext attacks. It is assumed that the attacker can get n plaintext and the corresponding ciphertext. Here we are actually referring to blocks. So this is important. The attacker gets n plaintext, but he has no choice over them. So you are giving them random n plaintext and the corresponding ciphertext, and from those information, the attacker gives you the secret key. This scenario is realistic in practice because the attacker may guess some blocks of the plaintext, and this is valid in practice because, for instance, consider some emails. The beginning headers are always fixed, so you can guess what they are. So if you see an encrypted email, you can guess the first few blocks. The attacker can also trick the key holder to encrypt a document which is known by the attacker. And in history, we have a lot of examples of this, especially in the Second World War. Also, the attacker can capture the device to provide any plaintext and store the corresponding ciphertext. So this is actually valid for the following attack types too, third and the fourth, which are chosen plaintext and the adaptively chosen plaintext. So let's move on to the chosen plaintext attack. The attacker is able to request the encryption of n plaintext of their choosing and captures the corresponding ciphertext. So this is important. And if you go back for the non-plaintext attack, linear cryptanalysis will be an example for this. But in the chosen text attacks, the attacker chooses the plaintext blocks they need. but not specifically telling which plain text, but maybe asks for plain text that has some property and captures the corresponding ciphertext. This is more unrealistic compared to the non-plain text attack. However, there are many examples in the history. Again, if you capture the device, then you can perform a chosen plain text attack. And let's move on to the fourth one, adaptively chosen plain text attacks. The attacker is able to request encryptions of some plain text, possibly seeing encryptions of some plain text first, making some calculations using them, and then ask for more. So this is more unrealistic compared to the other types, but again, if you capture a device, then since you can give any input you want and look at the output, then you can perform all of the attack types that we have discussed so far. And you might ask that if you capture the device, then you can also look inside it and capture the secret key too. But most of the time, the devices that come with cryptographic chips actually produced in a tamper-proof way. So if you try to open inside the device and try to read the ROM, they actually wipe the data inside it. So most of the time it is not possible. Think about a mobile phone. If you capture one and if it is locked and you need to perform you need to know the password, then here you can give the input you want, but you cannot open the mobile phone and see the key from there. So these were the attack types. Now let's look at the resource types. So the success of an attack is measured according to the resources it uses. First, time, we will call it the time complexity. The time or effort required to perform the attack. And memory complexity is the amount of memory or storage required to perform the attack. And finally, data is the amount of data required to perform the attack. So time, if the attack is really fast, you can give it in milliseconds, seconds, or days on the device that you perform the attack. But most of the time, we obtain results in a theoretical way. And it is not possible to perform the attack in practice, even if we can control all the computational devices in the whole world. So in this kind of scenarios, instead of trying to measure the time in years, we kind of give the time complexity as the amount of encryption operations we need to perform. So in theoretical attacks, you can see cryptanalysis results saying that we can break the cipher, for instance, if we can perform 2 to the 120 encryptions, which is actually not possible with today's technology. And memory complexity depends on, again, the attack, but here we generally give it as the number of blocks we need to store on the memory. So you can give it in terms of blocks or terabytes, gigabytes, depending on the size of the memory of the attack. And the data is the data we require to perform the attack. So we have seen some data types we need to perform the attack, like non-plain text or chosen plain text. Again, most of the time, since we are giving theoretical attacks, the data complexity most of the time are given like 2 to the 100 chosen plain text or non-plain text, and that kind of cryptanalysis results are very common in literature. So this is why in almost every cryptanalysis paper you can see these complexities at the beginning or at the end of the paper, given in a table and compared with the previously known results. So let's start with talking about some attack types, but we need to first consider the generic attacks to understand the non-generic ones. So we start with the exhaustive search, which is also known as brute force attack. If an attacker captures one plain text and the corresponding ciphertext, they can encrypt the plain text with every possible key and check if the correct ciphertext is observed. So actually, it is enough to capture only the ciphertext, The attacker can decrypt with every key and check if the obtained plaintext is something intelligible. So attack type is total break because you capture the secret key. Data type is ciphertext only because all you need is a single ciphertext block. But if you consider the scenario that is given here, then all you need is a one known plaintext. Time complex data is 2 to the k encryptions because the secret key is k bits, and in the worst case, you have to try every possible key, which is 2 to the k, and we are always considering the worst case scenario. So in the worst case, you have to perform 2 to the k encryptions. But of course, expected value is the half of this number. So if you perform the attack in practice, probably you need to do 2 to the k minus 1 encryptions. Memory none because you don't need to store anything actually. Again, I said data is one ciphertext block, but we can also say that it is one non-plain text. So as you can see, in this case, the cipher don't need to have a weakness at all. We can break every cipher with this attack because we are not interested in the internal structure of the cipher. All we need to capture is a one ciphertext block or maybe the corresponding plain text. And all we need to know the encryption or the decryption algorithm, and we try every possible key. So this way we can break every cipher. So this is why K has to be chosen large. And we already mentioned in our previous lectures, we always suggest 128-bit key, but currently sometimes we also use triple des, which has 112-bit security, which is also good for today's technology. Let's move on to the second generic attack called the table attack. In this attack type, we capture or pre-compute every plaintext and corresponding ciphertext. So imagine a scenario where you listen to the communication for a very long time, and if the block size is small, assuming a scenario that where you've seen every plaintext block and the corresponding ciphertext block, which are encrypted under a secret key which you don't know. So you capture this many information. So what you can do is that store them in a sorted table. So you have a table where plain text, every possible plain text are sorted, and the corresponding ciphertext listed in front of it, or the vice versa. You store the table with respect to every ciphertext block, and in front of them give the corresponding plain text block. So if you can do that, whenever you capture the ciphertext, you can go and look at this table and see what the plain text is, or you can use, if you want to send a message yourself, by looking at this table, you can generate the ciphertext you need from this table again. So in this case, in this attack, you don't know the key, but you have an algorithm that is equivalent to the encryption and the decryption. So this is why we call it a global deduction attack. Data type is non-plain text, but you have to know every possible plain text. So maybe saying that non-plain text is maybe irrelevant here, but you have to know every possible plain text and the corresponding ciphertext. Time is none, because if you have such a sorted table, all you need to do is just look at the table. So you're performing one lookup table, and even if the table is big, binary search algorithm is a logarithmic time algorithm. You can easily get the results in milliseconds or microseconds, so it is not a problem. So we say the time's complexity is none. Memory is 2 to the b blocks because we have to store every possible plain text, which is 2 to the b blocks, and actually we need to store the corresponding ciphertext. But if we order them if we keep the indices as if the plain text, then all we need to is to store the corresponding ciphertext block. So memory complexity is 2 to the b blocks. B is here the block size. And data is 2 to the b non-plain text, which is actually the all possible plain text blocks. So actually, at this point, this is important because if you go back to the exhaustive search attack, notice that time complexity is 2 to the k encryptions, and memory and data complexities are almost none. And in this case, at the table attack. Time complexity is none, but memory and data complexities are the highest that is actually possible, which are 2 to the B blocks and 2 to the B non-plain text. So if we can do something, anything in the middle of this, so actually I have a slide about this in a few slides later, but anything better than the combination of the exhaustive search and the table attack, we will call it a non-generic attack. So before going on, let's look at also time memory trade-offs. Classical version was introduced by Hellman in 1980. Even if we have enough computational power to perform the exhaustive search for a cipher with small key size, we have to perform 2 to the k encryptions every time to capture the key. So assume that somebody is using an algorithm which has a short key, and you can perform the exhaustive search attack for this algorithm, let's say in 3 months. So whenever you want to listen to a communication, you have to perform this exhaustive search all 3 months every time, which is not practical. So question is, can we do it only once and store some results on tables so that in the future we don't need to wait for 3 more months, but do it in a shorter time? So this can be done by time memory trade-off techniques. Idea is to perform exhaustive search in a clever way and store only a small part of the resulting tables. I said, for example, 4 terabytes because you can buy a hard drive that has 4 terabytes, but now that probably on the market you can even get 8 because these slides are a few years old. This is the pre-computation part, and for instance, for the A51 algorithm, you can do that. When performing the attack, attacker performs less than 2 to the k operations to obtain a value that is already in the table. So we have rainbow tables and different similar types of tables to perform the time memory trade-off attack. So it is just an exhaustive search, but done in a clever way, let's say. So you don't have to perform the same exhaustive search attack all the time. Okay. So let's move on to another thing that is we call the setting. So most of the time, we are focusing on the single key setting. So most attack scenarios consider that only one key is used during the whole communication, and the attacker tries to capture this key. So you might think that isn't it always the case? But no, because we don't suggest using the same key all the time. And we suggest changing the key from time to time, because once you use the same key for a very long time, you are leaking a lot of ciphertext, and maybe attacker also captures some plain text. So using it for a very long time might be a bad idea. This is why we, from time to time, suggest people to use update the key, especially if the block size is short. You might need to change your key frequently. But in such a case, if you're changing the keys and using for instance, if you use a secret key and change it once in a year, then we also suggest that these keys should be generated randomly. But if you're not doing that, and if you're generating a key that is related to the first one, for example, initially you chose a random key, and when you want to update it, let's say that you didn't want to generate a second one in a random way, but only incremented the key by one. So this means that the first key and the second key is somewhat related because you only incremented it by one. And in this kind of easy solutions actually causes problems in practice. And some attacks actually focuses on this scenarios where the different keys are used, but they are related. So related key setting is as follows. Using the same key for a long time can cause information leakage, and the secret key should be changed from time to time. If the used keys have some relations, then the attacker can exploit these relations to capture some or all of the used keys. So this is the idea. And let's briefly mention what the side channel analysis is, because probably for the rest of the course we won't be talking about it, but we need to know what it is. Such channel analysis is based on information gained from the physical implementation of a crypto system. Attacker requires a physical access to the device. Actually, this is most of the time. Sometimes you don't need to. For example, differential power analysis measures the power consumption of a device during encryption. Information leaks depending on the power used. For instance, XOR operation requires small amount of power, but an SBox operation requires a lot more. So a similar scenario where somebody is using AES, which we cannot break, and we claim that it is secure, but you are using it on a very small device. And if you have physical access to the device, as described in this example, you can check how much power this device consumes in a given time. And by looking at the power consumption, you can understand where the device performs an XOR operation and when it performs an SBox operation. And again, depending on the power it uses, you can capture the secret key. So in this case, you're not actually breaking the cipher because it does not have a weakness, but the implementation has a weakness. And in this case, it doesn't use the same amount of power for different types of operations. So side channel analysis, actually, these attacks do not break the cipher, but they break its implementation. And there are very different types of attacks. In this case, for instance, cache timing attacks are also side channel attacks. And in this case, all you need to have access to measure the time it requires to device to perform some operations. So in those attacks, maybe you may not even need a physical access to the device. So you don't need physically next to the device, but you might perform it from distance. So this is why in some cloud services, side channel attacks might become important. Okay, so let's finish it with this final slide. We talk about generic attacks, but then what are non-generic attacks? So exhaustive search provides an upper bound for security in terms of time complexity, which is 2 to the k. If the attacker captures 2 to the b minus 2 known plain text, so assume that you captured every plain text except 2, then the cipher should still be secure so that the attacker should be unable to distinguish the 2 remaining plain text and the cipher text. So any attack that requires less time than exhaustive search and less data and memory than the table attack is considered as the cryptanalysis of the cipher. If the attack requires resources that are not practical, for example, 2 to the 80 terabytes of storage, then it is called an academic break. And modern ciphers are most of the time designed in a good way, so we generally break them in an academic way. But if they have a very significant weakness, then you can sometimes break it in a practical way. It depends on the design, and sometimes this happens in lightweight designs because in the lightweight cryptography, we try to design it as simple and as small as possible, and sometimes we might overlook some properties which result in the cryptanalysis of the cipher. So this is how actually what cryptanalysis is called. But even in literature, we are not most of the time focusing on the cryptanalysis of the whole cipher. For instance, AES is of 10 rounds, and generally we cannot find an attack that breaks 10 rounds of AES, but we try to break shortened versions of AES, like 5 rounds, 6 rounds, and 7 rounds to see how secure the cipher is. And because the attacks are always getting better and better, so if we can break a cipher, the whole full cipher that is faster than exhaustive search, but still theoretical, then we kind of lose our confidence in the cipher, and we try to move on to something more secure.